Welcome to Spaceverse, your portal to cosmic adventures. NASA and SpaceX are facing challenges that stretch all the way to Jupiter, while Europe's newest rocket had an eventful debut. Timing is everything, and for America's leading space ventures, NASA and SpaceX, a series of unfortunate events couldn't have come at a worse time. On Thursday, July 11th, the SpaceX Falcon 9 rocket experienced a failure in its upper stage Merlin engine. This resulted in the loss of the mission payload, which was 20 of SpaceX's own Starlink satellites. This is particularly surprising given the Falcon 9's impressive track record. The rocket had flown 364 consecutive missions over nearly 8 years without any issues related to payload delivery. Although there have been a few booster crashes and tip-overs in the past, these incidents have become increasingly rare. The reusable stage of the vehicle performed flawlessly on this latest mission, achieving a textbook water landing. This marked SpaceX's 70th mission of the year so far, an unprecedented launch frequency. With 96 launches in 2023, SpaceX was on track to surpass that record. The rarity of such issues with the Falcon 9 makes this incident particularly noteworthy. For comparison, Russia's Soyuz variant, considered very reliable, flew 786 missions with a success rate of 97.3%. Now let's shift our focus to NASA. Recently, NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, experienced a technical glitch. The spacecraft's computer unexpectedly entered safe mode, causing it to suspend its scientific operations. This comes at a critical time, as Juno was scheduled to conduct a series of close flights of Jupiter's moon, Io. NASA engineers are working tirelessly to resolve the issue and get Juno back to full functionality. Meanwhile, over in Europe, the European Space Agency's newest rocket, the Ariane 6, had an eventful first flight. The rocket successfully lifted off, but not without some hiccups. During the launch, the rocket experienced unexpected vibrations and higher than anticipated temperatures. Despite these challenges, the Ariane 6 managed to deploy its payload into orbit, marking a significant milestone for ESA. The team is now analyzing the data to ensure that future flights can be more refined and reliable. In other news, the European Space Agency is dealing with the aftermath of its Vega C rocket's failed mission last December. The rocket, which was carrying 2 Earth observation satellites, deviated from its intended trajectory shortly after liftoff. An investigation revealed that a malfunction in the Zefiro 40 engine was to blame. ESA is now working with its industrial partners to address the issue and ensure the reliability of future Vega C launches. These setbacks highlight the challenges and risks inherent in space exploration. Every mission, no matter how routine it may seem, requires meticulous planning and execution. As technology advances and our ambitions grow, the stakes become higher and the room for error becomes smaller. Yet, it's these very challenges that drive innovation and progress in the field of space exploration. SpaceX has explained that the upper stage Merlin vacuum engine experienced a liquid oxygen leak during its initial burn towards orbital insertion. At T+4 minutes and 7 seconds, you can see an anomaly on the camera feed. The shiny, foil-like object you see is a radiant barrier, a thermal blanket that protects the engine's sensitive components, such as valves and sensors, from the radiant heat of the engine nozzle and the sun. It also prevents the kerosene liquid from freezing. Normally, you might notice puffs of gas beneath this barrier as the engine vents, but in this instance, a significant amount of material started leaking from the Merlin engine. This quickly resulted in an unusual buildup of ice crystals that formed, fell away, and were blasted by the engine exhaust. Despite this, the primary burn of the upper stage engine seemed unaffected and continued as usual until the end of the SpaceX livestream, which typically ends with the booster landing during a Starlink deployment. However, issues arose during the second burn of the upper stage. The engine failed to relight, which meant the vehicle couldn't circularize its orbit. This caused the perigee, or lowest point of the flight path, to drop to just 135 kilometers above the surface, less than half the intended altitude. Even so, the vehicle managed to deploy the 20 Starlink satellites. Now, atmospheric drag will begin pulling these satellites down into Earth's gravity well each time they pass through that low point, losing about 5 kilometers of altitude with each pass. The silver lining in this situation is that SpaceX now has an opportunity to experiment with the Starlink propulsion system. Elon Musk tweeted, "We're updating satellite software to run the ion thrusters at their equivalent of Warp 9. Unlike a Star Trek episode, this will probably not work, but it's worth a shot. The satellite thrusters need to raise orbit faster than the atmospheric drag pulls them down, or they burn up. Ironically, despite their name, ion thrusters have very low thrust capability. Their primary function is to gently adjust the satellite's position once it's already in orbit. This operation essentially delays the inevitable demise of the satellites, but it provides SpaceX with a valuable stress test to see how these thrusters perform under extreme conditions. The satellites will likely re-enter the atmosphere without issue, much like what happened in February 2022 when 49 Starlink satellites were hit by a geomagnetic storm and burnt up upon re-entry. The real problem now is that Falcon 9 is grounded until SpaceX can determine exactly what went wrong. This isn't cause for panic. SpaceX needs to diagnose the problem, devise a solution, and submit a report to the FAA. Once that's done, the rocket should be cleared for flight again. Normally, this wouldn't be a significant issue, but several high-profile missions are coming up soon. There's a cargo resupply mission to the ISS with a Cygnus spacecraft scheduled for early August. The Crew 9 mission set to take 4 NASA astronauts to the space station in mid-August, and Polaris Dawn, a crewed mission recently set to launch as early as July 31st, intended to push Falcon 9 and Dragon to their limits. These flights are unlikely to proceed until Falcon 9 is back in service and demonstrating reliability. However, this process can move quickly if SpaceX can clearly explain the issue, implement a fix, and resume flying 2 or 3 missions per week. Of course, this situation wouldn't be as critical if NASA had a functioning backup to the SpaceX launch system. Unfortunately, their only other crew capsule, the Boeing Starliner, remains troubled during its extended stay at the ISS and is unlikely to fly astronauts again anytime soon, if ever. NASA also relies on the heavy variant of the Falcon rocket for one of their most high-profile outer space exploration missions, the Europa Clipper. This mission, set to launch in October 2024, will embark on a 5-year journey to Jupiter's orbit to study the intriguing moon Europa. However, a new technical challenge could jeopardize the entire mission. On the same day SpaceX experienced their Falcon 9 issue, NASA released a statement about the Europa Clipper mission. While progress continues on the spacecraft, including the recent attachment of the high-gain antenna, a potentially faulty transistor in the Clipper's electronics poses a significant problem. These transistors, supplied by a contractor, are failing to meet the standards required to operate in the extreme environment of the outer solar system. According to NASA, testing data indicates some transistors are likely to fail in the high radiation environment near Jupiter and Europa because they are not as radiation resistant as expected. Jupiter's immense size and mass generate a powerful magnetic field 20,000 times stronger than Earth's. This field traps charged particles from the Sun, creating an intense radiation belt around Jupiter that Europa travels through. To study Europa, our spacecraft must pass through this radiation belt, making radiation-hardened electronics essential. It's particularly frustrating that this issue has arisen with such a critical mission. The Clipper mission profile is already designed to limit radiation exposure as much as possible. Instead of orbiting Europa closely, the spacecraft will follow a long elliptical path through the Jupiter system, dipping down to Europa once every few weeks before flying back out to escape the radiation belt. This strategy limits radiation exposure and allows the probe to gather and transmit more data. NASA's Europa Clipper is being constructed with a radiation vault to protect its sensitive electronics. This vault is located at the core of the spacecraft and is fortified with aluminum alloy walls that are 1/3 of an inch thick, providing a robust shield against the harsh radiation environment of the Jupiter system. The engineering team at NASA is currently focused on assessing the vulnerability of the transistors housed within this vault. They are investigating how many transistors might be susceptible to radiation damage and how these components are expected to perform during the mission. In their effort to ensure the Clipper's operational longevity, the team is exploring various strategies to maximize the durability of the transistors amidst Jupiter's intense radiation. These strategies are critical for maintaining the functionality and success of the mission. The agency is conducting a series of evaluations and tests, with a preliminary analysis of their findings anticipated to be completed by late July. This analysis will inform further design and protective measures, ensuring that the Clipper can endure its journey and effectively conduct its scientific mission to study Europa, one of Jupiter's moons. The grounding of Falcon 9 is not cause for panic. SpaceX needs to diagnose the problem, find a solution, and submit a report to the FAA. Once done, the rocket should be cleared for flight again. Normally, this wouldn't be a significant issue, but several high-profile missions are approaching quickly. There's a cargo resupply mission to the ISS with a Cygnus spacecraft scheduled for early August, the Crew 9 mission set to take 4 NASA astronauts to the space station in mid-August, and Polaris Dawn, a crewed mission recently set to launch as early as July 31st, intended to push Falcon 9 and Dragon to their limits. These flights are unlikely to proceed until Falcon 9 is back in service and demonstrating reliability. However, this process can move quickly if SpaceX can clearly explain the issue, implement a fix, and resume flying 2 or 3 missions per week. On July 9, 2024, Europe's space ambitions made a significant leap forward with the first flight of the Ariane 6 rocket from the Kourou launch site in French Guiana. This landmark event ushers in a new era for European space exploration. Although the launch faced a delay due to a data acquisition system issue, it ultimately proceeded smoothly. Just over 2 minutes into the flight, the solid boosters detached at an altitude of 62 kilometers. The Vulcan 2.1 engine, fueled by liquid hydrogen and oxygen, shut down as scheduled just under 8 minutes after liftoff. The first separation command took place 1 hour and 5 minutes into the flight, successfully deploying 3 satellites, OOV Cube, Curium-1, and Robusta-3A, into a circular orbit of 577 kilometers. Additionally, the YP-SAT and Peregrinus experiments attached to the upper stage were also successfully initiated. However, a significant issue with the auxiliary power unit impacted the Vinci engine's ability to reignite, which posed a considerable challenge to the mission's success. Despite this problem, the mission continued as planned, demonstrating the resilience and adaptability of the team involved. To ensure the safety and sustainability of the mission, a passivation maneuver for the upper stage was scheduled for 2 hours and 40 minutes into the flight. This maneuver was critical to deplete any remaining propellant and reduce the risk of explosion or collision with other objects in space. Following the passivation maneuver, the final phase of the mission was meticulously designed to guide the upper stage into a controlled re-entry. The components were programmed to re-enter the Earth's atmosphere and fall into the Pacific Ocean, where they would disintegrate upon re-entry or be safely submerged. This deorbit maneuver was crucial to mitigate space debris and ensure that the remnants of the mission did not pose a hazard to future space operations or terrestrial environments. The successful execution of this plan underscored the importance of thorough planning and the capability to handle unforeseen challenges during space missions. Ariane 6 is designed as an expendable rocket, a choice driven by Europe's relatively modest launch frequency of about 10 missions per year, reflecting a practical approach to current economic conditions. Nevertheless, Europe is already investing in future reusable rocket technologies with projects like Themis and Prometheus, aiming to introduce a reusable successor to Ariane 6 by the 2030s. Cost-effectiveness was a key factor in designing the Ariane 6. The 62 variant, featuring 2 solid side boosters, can launch up to 5,000 kilograms to geostationary transfer orbit at an estimated cost of $75 million per launch. This amounts to about $4,700 per kilogram to GTO, which is a 44% reduction compared to its predecessor, the Ariane 5. The more powerful 64 variant, with 4 side boosters, can lift up to 10,350 kilograms into low Earth orbit at a cost of approximately $85 million per launch, or roughly $8,200 per kilogram. Despite its advancements, the Ariane 6 faces tough competition from SpaceX, which provides launches to GTO at approximately $2,700 per kilogram. Hermann Ludwig Moeller from the European Space Policy Institute emphasizes that Ariane 6 plays a crucial role in maintaining Europe's position in the evolving space economy. The rocket aims to preserve Europe's ability to launch its own payloads independently and secure major commercial contracts. With over 30 missions already planned, including 18 for Amazon's Project Kuiper, Ariane 6 is set to make a significant impact. Following this successful debut flight, the launch schedule for Ariane 6 includes 1 more mission in 2024, 6 in 2025, and 8 in 2026. The objective is to achieve a consistent launch rate of around 10 missions per year once the rocket is fully certified. And that's it. Thanks for watching Spaceverse. Today, we explored the Ariane 6's historic launch and its role in Europe's space future, and we looked at the challenges facing SpaceX's Falcon 9. Don't forget to like, subscribe, and hit the bell for more space updates. See you next time.